It's time to go into a little bit more detail with this problem. I'm going to turn it on its side. We're going to figure out how mechanical work and electrical energy are related. And to do that, I need a resistor. Let's put it in a light bulb. And I need a wire that goes this way, and a wire that goes this way, and I need a magnetic field. And I don't want to waste your time, so I'm just going to draw a few magnetic field vectors. My magnetic field is going to be always out, let's say. And I am hoping to make the magnetic field uniform. I'm not trying to space these guys differently. And there's probably magnetic field out here too. This is not a magnetic field that is created by our setup. This is a magnetic field that has existed for some other reason. Maybe our whole setup is near a magnet, or our whole setup is inside a solenoid or something. But you've got this huge external magnetic field sitting right there. And I'm just going to call it B for our purposes. Next, I need a rod, and it is metal. A conductive metal. It does not need to be ferromagnetic, but I'm going to put it here in the field and connecting the two wires. So you got a hole here, and you got a hole there, and you've got a solid cylinder that you can then push from one side to another. It doesn't really want to move because you know that you've got some Lenz's law that would resist any kind of push that you could get. But my plan is to push the rod this direction, and this is going to be my force external, or my applied force. I'm going to be pushing that direction and push at speed V. That's my plan. And I guess I also need the distance apart these two guys are, because I'm going to be talking about area in a little bit. So my first argument is that flux at this instant right here is magnetic field dotted into area. Notice that the magnetic field is pointing this way and the area is pointing this way or that way, so we don't have to do any cosines. But I'm finding that to be magnetic field times, well, going to be times area, but the area is the length times the width, but the width is changing all the time. So what if instead I looked for delta phi? So delta phi is going to be the magnetic field, which is constant, so I don't have to delta that sucker. It's like pulling it out of a derivative. And then I'm going to say that the change in width is just the, it's going to be the change in time times the velocity. That's the change in width, and then I need to multiply that by the length, and I've found the area. So see if this makes sense to you. I'm trying to find the change in area, and so that should be, it should be the width, or change in width, which is delta t times v, multiplied by the length, all right? That direction. Now, I want to find the induced voltage. And induced voltage is negative n times d phi dt, or if we're not doing the integral formulation, and acknowledging also that n is just 1 in this case, I'm just going to have negative b times delta t times v times L divided by delta t. Oh goody! The time comes out of the equation, and we find that the induced voltage is B times V times L. Be careful in your notes. Induced voltage needs to be a capital V, and the velocity needs to be a lowercase v. So I like to put a little wing right there on those velocities. Make sure that you're doing that also. And this is just BVL. Now let's think about what direction the voltage will be induced. There will be a voltage induced here because the area is increasing in this case, and it's seeing more and more flux that direction. Will it like that? No, this minus sign is Lenz's law, and it says, don't change my flux. Because that loop is a flux capacitor, and Lenz's law says I want the flux to remain exactly as it was. And so we pull this direction, or pushing that direction, and the area is increasing, and so it's getting more and more flux up, and we want to make some flux down to counteract that, so we're going to make a current go this direction. I assert that the induced current goes clockwise in this case. check it, make sure that you get the same answer. You could also do it as the charge is moving this direction in a magnetic field that's up and use this right-hand rule too. I don't care how you do it. But my point is the induced voltage, remember, the induced voltage is a magnetic field because V is negative ed. So if we were trying to find the electric field is, check this out, the electric field, if V is negative ed, and V is also negative BVL, we're going to find the electric field to simply be B times, wait a second, what is this D? The electric field exists inside this rod. That's where the electric field will be existing. That's because that's where the motion is. That's what's changing the area. So that distance, that L, is L, and this distance here, this D, should also be L. So let me write this again. This is negative EL, and I'm going to say that E then is, well, it's BVL divided by L, which is B times V. And that's such a pleasant result that I'll write it again. Electric field induced is the magnetic field times how fast you're going. So let's review. If you take a piece of metal and you move it in a magnetic field, you will get an electric field in that metal that's at a right angle to the speed, at the velocity, and a right angle to the magnetic field. That is automatic. Every time metal moves, it doesn't need to be connected through a loop or anything. Anytime metal moves, we induce an electric field inside of that metal. But this is a really useful way of doing that because our electric field now can create a current. So let's see what it does. We know that V is IR, and I hope that, well, what should I do? I should copy my results down right here. I'm going to say that we know the electric field is BVL over V, which is B times V, and we also know that the induced voltage is BVL. And I'm disregarding for a moment the direction of the induced voltage. And now I want to keep this picture here so that we can continue considering what's going on here. We're pushing with an external force, and I want to think about what, well, I want to think about current through the bulb. You know that since we've got a light bulb here and it's got a certain resistance, we know that V is equal to I times R. And so the current going through is simply the voltage, sorry, capital V, divided by the resistance. And the voltage is BVL, so BVL divided by that resistance. Now, I might also be interested in finding what the force is. What about the force? Force to keep it moving. That force to keep it moving is probably Bill, right? Because if the wire is moving in a magnetic field, then there's a force on the charges. There's a force actually on the wire as a result of the force on the charges. So to keep it moving, I need to counteract that force because I'm arguing that there's a force the other direction. This is the magnetic force on the wire, and it's B, well, what did we say? It was B times I times L. And this L right here is the same L. So the force to keep it moving is B times I times L. And I know what I is. It's BVL over R. So I can plug that sucker in, and I think I get B times BVL over R times L. This stuff right here being what we just inserted, and if I combine them, I get B squared times V times L squared divided by R. And you know that there's only one thing in the numerator that's not squared, and that does not make me comfortable. Ha 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 ha, how can we square that V? Oh, power is force times velocity, isn't it? Yes, it is. So let's find the power that you are exerting in order to keep that bar moving. Yeah, it requires a constant input of energy because the bar would like to stop. The bar would like to stop because this is magnetic braking. This is why your Prius is awesome, because there's energy contained in the motion right here, and because this is lighting a light bulb, bar would very much like to stop. Of course, if there weren't a light bulb here, oh my gosh, it would actually be impossible. If there were no resistance at all, it would be impossible to move that rod. That's an interesting issue. Or maybe it would create more and more and more and more current, and you could get yourself an infinite current if you kept moving it that direction because it wants to keep the magnetic field that it has. And superconductors can actually achieve that goal. They can keep it. But that's a tangent. We need to multiply that force by velocity, so I get B squared times V times L squared over R times V, which is B squared times V squared times L squared divided by R. That is the mechanical power. The mechanical power is the mechanical force that we have to use to keep it moving, times the speed at which we're moving it, and that's the number that we get. It's beautiful, right? Got a whole bunch of square stuff in the numerator. But I'm interested now in the electrical power. Power electrical to the bulb, right? Wouldn't that be an interesting question also? Electrical power, well, you can see it any way you want. You want to call it I squared R? Sure, that's fine with me. The joule heating, the energy delivered per second to this resistor because of the current that's going through it and lighting up the light bulb. Let's take I. What's I here? We're going to square that sucker right there. I got BVL divided by R, and I'm going to square it. And then I have to multiply the whole thing by R. Dun, dun, dun. You ready for this? It's B squared times V squared times L squared divided by R. We have just concluded that the power that the bulb gets is exactly equal to the power that we're putting into the system by pushing this dang thing. We've created a generator. We put energy in, and energy comes out as light and heat from a bulb. And these are the same thing. I'm impressed. I think that's really fun. Don't you guys think? Look at that. Isn't that pretty? Yeah. I don't want to waste your time, so I'm just going to draw a few magnetic field vectors. My magnetic field is going to be always out, let's say. And I am hoping to make the magnetic field uniform. I'm not trying to space these guys differently. And there's probably magnetic field out here too. This is not a magnetic field that is created by our setup. This is a magnetic field that has existed for some other reason. Maybe the field and connecting the two wires. So you got a hole here, and you got a hole there, and you've got a solid cylinder that you can then push from one side to another. It doesn't really want to move because you know that you've got some Lenz's law that would resist any kind of. It's time to go into a little bit more detail with this problem. I'm going to turn it on its side. We're going to figure out how mechanical work and electrical energy are related. And to do that, I need a resistor. Let's put it in a light bulb. And I need a wire that goes this way, and a wire that goes this way, and I need a magnetic field and push that you could get. But my plan is to push the rod this direction, and this is going to be my force external, or my applied force. I'm going to be pushing that direction and push at speed V. That be our whole setup is near a magnet, or our whole setup is inside a solenoid or something. But you've got this huge external magnetic field sitting right there, and I'm just going to call it B for our purposes. Next, I need a rod, and it is metal, a conductive metal. It does not need to be ferromagnetic, but I'm going to put it here in